Right. Good evening, everyone. Everyone in person and everyone on YouTube, hello. So this will be being recorded if anyone wants to catch up after the fact. I need to remember to talk slowly. Sorry about that. Hello. I'm Sammy. I'm a principal technical consultant at ECS. We're soon to become GlobalLogic UK and Ireland, but today we're still ECS officially. I lead the data science team at ECS, and today we've also got Nick. Do you want to introduce yourself, Nick?
Yep. So hi, my name's Nick. I'm a senior data scientist. So I've been at ECS for about 3 months now, I think. And yeah, so I'll be going through the lab session of this. So we'll be doing some interactive coding after Sammy's slides.
Yep. So today we have hijacked the DevOps Playground to do data science instead. Thank you, Patrick, for giving us a slot to talk about data science. We've assumed no knowledge, and we want to give a really, really fundamental introduction to data science and machine learning, and starting from scratch and writing a very, very first machine learning model. We're going to use a canonical, as we would say, but like a gold standard data set and approach. MNIST, it's a series of handwritten digits that you're trying to work out, is this a 1, is this a 2? And we're making a very, very simple machine learning model to demonstrate how to do this. We are ECS Data Science. On the right-hand side, you can see us presenting to some customers at our AWS Immersion Day, where we explained how data science and machine learning can be used on AWS particularly efficiently. Today, we won't be using AWS. We'll be using a Google service called Collab. They have given, for some reason, free access to a cloud environment to run Jupyter Notebooks, which is the way that data scientists run code. So data science is made up of very open source technology, and AWS just happens to be a convenient wrapper around them that we talk about on this day. But so does Google, so today we'll be using Google's wrapper. We're a team of 7. We are hiring. If you're interested and you think you might fit one of our job descriptions, please reach out to one of us. If you're in person, you can come to myself, Sammy, or if you're in the comments, I think there's a careers at ECS email. There's definitely an email that you can contact there. I'm sure somebody will help you out if you'd like to make yourself known to us. We work across a wide variety of different industries, from energy to financial services. I'm more than happy to talk about some of the work that we've done in the past. There are some use cases that we have done, sort of classical use cases for machine learning that we've done in customer use cases. I'll talk about later on. We work with clients right at the beginning of their journey, so just as they're starting to understand that they have this data available, but they need to get it to the cloud, right up until those that have very established data science teams, hundreds strong, how to make that workflow more efficient, how to share technology with each other, and want to improve, and how to do that. We call that enablement. So we do data science enablement as well. What is data science? This is a super broad general definition because there isn't a very good definition of data science. Ultimately, if you are a data scientist, you do data science, and that can mean lots of things to many different people. Our definition is it's the use of models and statistics to draw insights from data, which involves collecting data, finding common patterns in that data, creating predictions of those patterns, and solving business problems. That's the main thing that we bring to this as consultant data scientists. So an example, I'm going to collect the order history of your purchase on Amazon. I'm going to see if there's a pattern in the purchases that you and similar people like you, or even just personalized to your own predictions, to your own activity. See if there's any pattern there. I buy a newspaper on the first day of the month. Okay, well, I could recommend a subscription for that, for instance. I might predict that you would keep doing this, or I might try and predict what other products might be relevant to you. And this business problem might be we want to keep customers on the platform, recommend solutions to them. Things like Amazon recommending Amazon Basics things. So they look at what sells popularly across their customer base and take something like that and make a really super basic but cheap version of it that also does reasonably well because Amazon has the scale of Amazon. So that's an example of what data science can do. There's loads of stuff that data science can do. It's an art. It's got the word science in it. The scientific bit is how we approach doing data science. So it's a scientific method. So I have a science background. Nick also has a science background. That's quite common in our field. It's not necessary, but a lot of our data scientists have scientific backgrounds. You take a hypothesis about what machine learning model might work, what approach might work, what data set might be there. The client might have no idea what they have. You might know it's a shipping company, but you don't know anything else. So you think, okay, I think they have this data. I think it will be systematic or repeatable. I think I'm going to be able to make predictions on this. In my very first projects at my previous consultancy company, I knew that this customer had time series data, so like a time series over time of the energy usage of customers. I knew that there would be customer groups, but I didn't know any more than that. I didn't know if there was going to be a pattern in it. I needed to look at the data firsthand to see if there was any clear pattern in there. And I needed to solve this business problem. And in this case, the business problem was people are leaving the premises and not paying their last bill. So could I detect this? Could I detect an unusual or anomaly detection on this type of data? And not just anomaly detection, because there are 2 types of anomaly. Amazon, when selling on the internet, will have a huge spike of orders on Black Friday. But that's not an anomaly, that's expected. It is anomalous. So there's a slightly small distinction to be made there. We didn't want to flood these human analysts with a crazy amount of this information that they would not be able to process because, well, they're humans, unfortunately. We haven't quite yet automated all the humans away. Thankfully, we still have jobs. Data scientists are jacks of all trades. So what do I mean by that? We have expertise and specialty across the entire gamut of data, which can involve everything from loading data, doing data engineering, basic data engineering on this data, building a cloud environment using basic solution architecture or DevOps skills to actually do the data analysis, doing the data analysis itself, doing business intelligence or a data analysis on top of that, machine learning engineering, R&D could be part of it as well, and then to productionize or get the code to run at scale in the cloud. You would then start to be delving into the domain of MLOps, machine learning operations, to speed up your code. Even AIOps is now a field as well. And we have to do all of it. And we have to do it at a very ambitious timescale. There's a slide later on that explains our standard approach. But within 4 weeks, we'd go from never having spoken to the customer before to here's your machine learning model that could do the business problem. If we took a bit more time and built the environment that would scale, this would solve your problem in production. And that's ambitious. And we go into it not knowing what we might find. We can't assume anything. The customer might have less data than they said they had. That happens very often. The customer might have no data. That also happens very often, unfortunately. Yeah. However, at every stage, somebody else could have done our job better. It's just that we could do all of it. And we know that we can do it on the timescale and then hand over something that is useful to the customer. I've talked about the definition of data science, but yeah, data science means lots of things, lots of people. I will not admit to who it was, but I have spoken to some data scientists in places that I like, how did you get this title? So enough of that. How does machine learning work? Okay, there's no way we could possibly go into the intricacies of machine learning, and to be honest, there's people better than me who've explained better than I possibly could in infinite time how this works. It's a methodology for training models to understand insights from data. So machine learning is a 2-year-old. So you want a 2-year-old to find the green thing or the red thing. Machine learning can figure out how to do that. So if there's a really obvious pattern, we want the machine learning model. We will train an algorithm using machine learning to be able to pick apart this pattern. So in this example, we have data that is age, gender, salary, and whether they defaulted on their loan. So this is financial data. This is potentially a bank or a loan company. And they have historic data. So this is things that actually happened. And they would like to work out in the future who is and who's not going to do this because they don't want people who are not going to pay their money, their loans off, unsurprisingly. There are lots of reasons that they could have defaulted. We don't have those reasons. We don't know if the reason is they suddenly fell ill or they changed job to a lower paying job. We don't know. We just have this current data. In fact, this may not even be current. We just know that this is the data that's there and they defaulted on the loan at some point. So we've got a section above and a section below. So in this section, we're talking about like kind of the non-ML approach. So you could just make a bunch of rules. You could just draw a bunch of lines and say, okay, if you're older than 30, you will not default because this guy is older than 30 and did not default. That's quite restrictive. And obviously you need to have somebody type in one of these rules every time. And that can get very tedious. But also, are you going to make one for every customer? What about the customer that comes along, you don't have any data? For instance, this female. We don't have any data for what how women might affect, being a woman might affect your likelihood or non-likelihood to default on a loan. We don't know whether the impact is worse or good. This person also earns more than the other 2 people in the data set. So is that good? It probably is, but we don't know that. And so these rules do not cover that situation. So we would not be able to make a prediction for this person. And if you were that person, you might feel excluded, that we did not give back to you about whether you could or could not get a loan. You can understand why that's particularly topical in 2022. But to be honest, it shouldn't have been an issue anyway. Machine learning can solve these issues if done right. So in this case, we've got something called Xgboost. It's a very popular machine learning technique and creates models that can be classifiers for making whether you're trying to detect a 1 or a 0. So this person is definitely going to default, this person is definitely not going to default. So a yes or no sort of question. It can do multiple different classes. In the example later, we'll be detecting which digit did this person write, and we're trying to make a model that does that. And we want it to be done automatically. How Xgboost does it, I'm not going to go into the specifics, there's really good documentation online, but it basically draws a bunch of these automatically. It tries to divide the data sets down based on decision trees, and it joins together a bunch of these different decision trees and tries to come up with the one that solves the question the best. How it decides how it's done well, that's the machine learning bit. So the model is the rules, and how it refines to become really good at its job is the machine learning bit. We're going to see some of that later in the training section of the model later in the demo, and we can go into more detail if you'd like as well. The important part is, in spite of the fact that there was no data about women in the data set, before the model was trained. So at this point, this is the data that was used to train the model. In spite of that, we've been able to make a prediction that this person was not likely to default on their loan, although there is a confidence score associated with that prediction. Because it's predicting outside of the bounds of some of the data that it's seen, this person earns more than the top maximum data that was in the data set. It's not confident about its prediction, and the confidence is usually a rating between 0 and 1. Welcome. Is a rating between 0 and 100, or 0 and 1. But it's still being able to make a prediction. In reality, you probably don't want to just throw a prediction that is very unconfident. An example, lateral flow tests are between 68 and a bit more than that % accurate. You don't want to just on the lateral flow test say you definitely have COVID. It's likely, and then you'd have a PCR test which is much, much more accurate. So in this case, our equivalent of that is, this is your like basic broad brush differentiator, but actually what might happen is, let's take anybody who gets a confidence below 80% and have a person review the machine learning model output. We call that semi-supervised learning. It's one of the techniques that can be used to still give an answer when that model is confident and then get better over time, but also not give a bad prediction. I forgot about those. So this is the salesy slide. I promise I won't. I'm just using it as a template to talk over. I won't be going over the sales procedure here. We are interested in working with people at all stages of their data journey. If you do want to reach out for a sales conversation, please let me know. However, this is to illustrate what we will be doing today within the grand scheme of how data science works, at least for us. So what we do with our clients is we offer this one-day workshop called a value stream assessment. We ask them, what use cases do you think you have? What data do you think you have? Do you know what data you have? Could we get access to this data? Is there a restriction of us using this data? What machine learning models have you considered using? Have you got any canonical examples of machine learning, like time series forecasting, that you would like us to look into? What platform do you have available? Do you use AWS? Do you use GCP? All of those sorts of questions. And we'll come up with a matrix of opportunity. So how feasible is it to do the use case? As in, how difficult is it with going this way, being more difficult? And how much value would it bring to the business if we succeed? And we pick the one that is the maximum value with the lowest difficulty as the lowest hanging fruit, the min-max, the starting point to the journey. We take that and we do 1 week of looking at the data. So we actually get the data. This is where we find out, is it really what the client said? Is there really a pattern in here? Is there something more interesting here? We also just look at the data, and honestly, we found things in this stage of the project that have been useful for our clients, just us sanity checking our understanding of the data. I can give you one example. One of the companies I worked at, I was predicting the yield of output of a chemical plant, and it's between 0 and 100%, and they want to know when it's getting worse so that they can do maintenance on this plant. And they sold different recipes for making this chemical. The most expensive and state-of-the-art one was worse than the cheapest one. And they didn't know until somebody put together all the data and actually looked at the comparison. And there were a few reasons why this did not happen, but it doesn't really matter. I was the first person to see it. I put it on my slide to say, hey, does this make sense? It's a bit surprising to me. It's like, oh. And the exact comment was, maybe we shouldn't tell our customers this, which I thought was an interesting way of putting it. But anyway, once you've looked at this, you have some idea about what machine learning approach you might use. For time series forecasting, you might be like, I'm going to use DeepAR, which is Amazon's way of doing a very good model that Amazon supplies for free to use for time series forecasting. And we then would move to this stage, the proof of concept, where we actually train this data, train the model on the data. This can be 4 weeks long, depends how large the data sets are. We would constrain usually to a snapshot of data. So this client might be getting hundreds and hundreds of thousands of data points a day, but we might just take one of their data as an example and say, let's show that we could do it on this. Let's go with them and say, the exam question is, can we save you money? The answer is probably, because we've got a model that works on the initial data set. However, this is the DevOps bit. This is the expensive bit. This is the hard bit. This is the part that's hard for you to convince your boss that you need to pay for. Whereas you've, in only a few weeks, and not very much money actually, got on a machine learning model that works, verifiably works, on some data it hasn't seen before. We keep some data back, and Nick will talk about that later on. But it hasn't yet been put into production. And more importantly than that, it hasn't yet been given, the people who would use the tool, who need to use the tool to benefit from the tool, have not yet been upskilled, or it's not being operationalized. It's not being put into the way of working of those people. And that's hard. That's cultural fit stuff. If you want examples of this going badly, try convincing a doctor that the iPad with the algorithm on it knows more about it than them having studied 20 years and worked in the field for 20 years. It might do, but convincing them and the patient to trust this iPad and whatever's running on it, it's going to be a very difficult battle. And you have to do that as part of the production bit. You just having them all there in the cloud waiting for predictions is useless if it's not actually saving you the money. So it's that point where we start to be a bit more, let's make sure this doesn't fail. An example where models can fail, COVID-19. Caught everyone off guard. some, okay, almost everyone I've got. Airlines, their pricing model was like, I need to sell these tickets, but no one is buying them, so I'm going to keep decreasing the price. I'm going to keep decreasing the price, and they went to like near zero. The people who were buying tickets had a legal right to do so and needed to travel. They would have paid any amount of money to do that. But the model was, these tickets are not selling, so I will keep reducing the price. That's an example where machine learning can go wrong. You need to be able to guard against that. And there are techniques, things like data drift detection, model monitoring, model debugging, that you can use to make sure this doesn't happen. But that's an expensive hard part. So we show that the approach works. We get our customers data-driven and savvy before we take them through that part of the journey. Today, we're focusing on this bit. So I think Nick was ambitious on how far through the POC phase we'll be doing in less than an hour, but we'll end up with a POC that would work. There are other approaches that you could use that are much more advanced than the approach that we're going to choose today. We're choosing one of the simplest approaches possible to just get your feet wet and get started. Many people have tried working machine learning on this data set and think it may well be a Kaggle problem. So there's a leaderboard of how well people are doing at this, and you'll look at some of the most interesting and advanced techniques and say, how did you come up with this? People spend months just doing this leaderboard because you get cash prizes if you do particularly well. It's a great badge to wear and say, I am so impressive I came in the top 200 worldwide at this. Sadly, I don't have this badge, unfortunately. But the right-hand side of that wedge, we are open to the idea of doing a machine learning ops or ML ops playground later, where we would take not necessarily this model, but something like this, and maybe the output that you would get from a data scientist, the sort that you might be generating today, and then actually take it to production to actually give a very simple architecture about how would you get this model that is on my laptop, how would you get it to somewhere where anyone in the world can throw some data at it and get a result out. So we're open to doing one of those, so please let me know if you have interest, because I need to convince my friends here that we need to do another takeover of their playground situation. Right, so today we're going to train a handwritten image recognition machine learning model using Google Collab, Python, and Scikit-learn. Nick will probably go into more detail about each of these things, but I'll go over a little bit. So handwritten images, so this MNIST data set, people have drawn 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 in a small box, a 28 by 28 pixel box. We want to try and predict what a new digit that somebody would write at any time would be, also within this very small framework. So we want to be able to handle unseen data, so we're going to have something to check that we can do that in the future. It is going to use machine learning to get better at working out which of these are correct. So we do have labels in this case. We're lucky for this. Sometimes we don't have labels. So we would have the digits, but we don't know what is a 1, what is a 2, what is a 3. In this case, we have 1, and something next to us telling us that's a 1. And we have lots and lots and lots of examples of that. And this is necessary. If you don't have this, you don't know how well you're doing. So that's one of the data points that this machine learning model is going to use to do the machine learning part. We're going to use Google Collab. I think I mentioned this earlier. The way that data scientists use Python is using something called Jupyter Notebooks, typically, especially for development. And Google Collab is, for some reason, Google has given a free environment to do this. It's super easy to quick start. You need a Google account, but I presume everyone has one. And you just open whatever, it's collab.research.google.com, I think. We have the URL, we'll show you later on. Open that up, and you can immediately start running stuff, even with GPU acceleration, which is absurd that they would give you this for free. I don't know why. Amazon will probably charge you $1 per hour for the same thing. It's like, why is Google doing this? Thank you, Google. Anyway, that's all I can say, really. And Scikit-learn. Scikit-learn is a framework, an open source framework for machine learning that is very popular and very powerful. And there are lots and lots of different models that you can use using Scikit-learn. Everything, like the entire gamut of shallow machine learning, let's say. You can get into more complicated architectures that are more like how the brain works using deep learning approaches. Those start to use frameworks such as TensorFlow and PyTorch. Today we'll just be using the Scikit-learn, which can be very powerful. The guy who maintains this, who I believe his name is Gael, G-A-E-L, I can't remember what his surname is. He gives these talks every year about why are you jumping to deep learning? Machine learning is perfectly adequate on this. And in fact, I should also state that if your model can be done without machine learning, you should do it without machine learning. I can give you a very fun example from a colleague of mine. He outperformed every machine learning and deep learning model that he tried to make on a particular use case with a single line of code, which was just an if statement. And it outperformed everything with all very hard research technology. They spent 6 months, and this single line of code outperformed everything. And that was what went into the production for the client. It was better than everything else that they could do. Right, I've got some examples of use cases here. Dynamic pricing system for car insurance. So this is one of our case studies. And I put GlobalLogic UK&I because that's what our name will be in like 3 days' time. So we have customer historical data from the past few years. This is who made claims on of their cars. So we know males of this age who drive this type of car, who live in this part of the country, have accidents at this rate. We may even know specifically for one person if we have enough data. But what we can do is we can train a machine learning model to predict how much money are you going to cost the company and price that in. So rather than just having buckets of information, we can say, okay, men cost more than women, for instance. You can have it be, okay, no, this specific category of person is more likely to have a car crash than this one, so let's charge them a few pounds more a year in the premium, and that will average out. An example of this going wrong, I wish I could remember the name of the company. If you were born on a Sunday, your premium was £40 less a year than if you were born on a Monday, because they didn't constrain their model to avoid this problem. So it can go wrong if you don't think about what you're doing, and that can be something that would catch you off guard. Why would that be something the model would use? But for this model to get very accurate, it used the day in which you were born for some reason. Transcript processing for call centers. So one of our main plays in our company is Amazon Connect. It's an internet-connected call center built in AWS that you can then use all other data science techniques that you also use on AWS and connect them quite nicely together, no pun intended. In this example, we have call center transcripts. What did you say that you were calling about, and what did you have your conversation about? We use natural language processing, NLP, to understand this data set. One of the most basic examples of what you can do here is just have a vector, just a bunch of zeros, and if a word is said, then just put a 1 in that position. So you can have a vector for every unique word in the English language, and if they say the word and, you put a 1 in the column representing that word. That's a very long amount of data. It's very sparse, meaning that most of the data will be no, because most words are not said ever, let alone within a particular sentence. So there are more complex techniques called word embeddings. And in this case, we used BERT sentence embeddings. BERT is a very funny acronym. There's also that in the research field. There's the two main competitors, BERT and Elmo. And Nick told me that the French version of BERT is called Camembert, which I think is a very nice name. If you've heard about GPT-3, that's another embedding-based approach. It's a very different type of approach using something called transformers. I'm more than happy to talk about that another time. But all of these represent the data in a slightly different way, but a more powerful way. So we did something that basically takes these transcripts, processes it in the way I described, and then highlights themes of discussion, and also whether the people were positive sentiment or negative sentiment. So these people are calling today about the card, and they're negative, and they're based in Scotland. And yesterday they weren't negative, so it's not just a Scottish thing. It's that specifically today their cards are not working. So maybe we should do something about that. That's an example of the sort of insight that might fall out of this, that a human analyst may not be able to see enough data points to get to put together this pattern. Health and safety document classification. So one of my colleagues worked on when a health issue happens in the large workplaces, you have to file a report that explains what happened, and also do something about it happening again. One of the examples, I don't know if it's on here, of the theme that came out was, okay, so what this person did, he looked at the report, the text of the report, processed this in a very similar way that I described on the previous slide, and highlighted common pairs of words that were coming up very often in these tickets and costing the company a lot of money because they had to pay out to compensate the people who were injured. So one of the most common pairs of words that came out was like wet floor, or floor sign, or wet floor sign. And the reason for that was if you didn't put a wet floor sign, then person fell and they would blame the company because there was no notification about that. Another one that came out was Yorkshire puddings. I want to ask everyone in the room, and if everyone on YouTube, if you can comment, why the word Yorkshire puddings would come up quite frequently and cost a company quite a lot of money. It's the second biggest problem after the wet floor sign. Anyone have any ideas in this room who isn't wearing a blue shirt? Any idea at all?
High temperature and fat.
Very close, very, very close. So what would the injury be if it was high temperature and fat? Burns. So correct, 100 points to this person. I'm not sure if these points mean anything. We need to figure out if we can give this person a prize. Well done. So legitimately, it turns out that as you pulled the Yorkshire puddings out of the oven, it was full of explosive fat that would just literally explode and cover the people in boiling oil. Very painful third-degree burns. And the solution was, A, turn off the oven before you do that, and B, there's some gloves that they put on and some like mask or something. That was something they did not know. They didn't know this. Because of course it was happening, but not the scale that it was happening. It was happening across multiple different sites. If you imagine it was like a Wetherspoons, like every site in the UK would have this issue, but not all of them together. Until you put everything together, you wouldn't know that it was a systematic problem. So that's a funny example, but it's a true example of how machine learning helped. And finally, we can create personalized offerings. I talked a little bit about that in the financial data earlier, but you get these customer resource management data sets. So basically what the analyst on the other end of the phone is typing in when you say, I'd like to change my address, please. So that database and what financial products they subscribe to. So for instance, do you have a mortgage with this company? Do you have a loan with this company? Do you have a credit card with this company? We put this into a machine learning model along with things like, are you male? Are you based in the UK? All that sort of stuff. How many accounts do you have? You group them into different types of segments. You can either do something like this, or you can these patterns, these groups that have fallen out here, they can actually organically fall out of the data. So it turns out that people who live in London between 18 and 30 who have a particular credit card might be people who are young tech savvy. Like it might just fall out like that, but the groupings are made in an unbiased way based on the data. Using something called K-means clustering, you could achieve something like this. These techniques do not require labels. You don't need to say, this person is young tech savvy, find me more people like this. This is just group me these by similarity and make it so that if a new person came along and they arrived here, they would be classed as young tech savvy, for instance. So what this could be used for is, oh, I see this segment over here, and we're not selling anything to them. Maybe we should create a product that works for them. An example for a financial product that was created for this exact reason was streamers, YouTube and Twitch streamers, and other influencers were being denied loans and credit cards because banks don't believe this is a job, even though some of these people are some of the richest people in the world. And that's a segment that you could capture. And there was an app, I wish I could remember the name, I don't remember off the top of my head, that was created specifically for these people because they couldn't get a credit rating of the right type from other businesses. So that's an example there. And yeah, that would be matching the best financial products, even a hypothetically new one, to the right type of customer. So another person calls in and they're an influencer. Oh, have you tried our influencer package? No? Okay, cool. Go talk about it to your millions of subscribers and make all of your young kids subscribe to it. Failures of ML. Right, so there are lots of examples that I could talk about. I've used this one because our symbol is a panda. So I could talk about that. And funnily enough, one of the main data science technologies that we use is called Pandas to load in tabular data. It's one of the most popular open source packages used for data science by quite some distance. There are examples where there was a stop sign and people put lines of tape that obscure the sign in some way that we can clearly see it's still a stop sign with some black tape on it, but it caused the Tesla to think it was an 80-mile-per-hour speed limit sign and it just went straight through the stop sign. If you're not very careful with machine learning, it can go horribly wrong. And in this particular example, we're going to show an adversarial example. So we have a panda. The model is 57% confidence. Has everyone said that this is a panda? How confident is everyone on a scale of 1 to 100? Yeah? Okay. So we're adding this noise. It's just some noise, 0.007 of this weighting of noise. So you barely can see this. And clearly this is a gibbon. These people who thought it was a panda, completely wrong. How could you possibly get it so wrong? You can see it looks almost identical. There's nothing, you can't see anything in that image that is not a panda, but this machine learning model can. There are examples of image recognition models that recognize the snow in the picture of penguins as penguins rather than the penguin in the picture of the penguin, because the model, it's hard to constrain the model to make it do something, because you can't really influence the training step in this specific way. You can just say, okay, here's the maths behind it, this is the image I want you to detect, and this is the label of that image, go nuts, and it will just do it. And if you aren't careful, these sorts of things can happen. If you have used the internet lately and you've been told to fill in, like select which parts of this image are crosswalks or whatever, if you've noticed an increasing amount of noise being put in there, this is literally this exact reason, that they're trying to make their image recognition models robust against this type of manipulation. That's the totality of everything I had to present today. I want to ask first if there's any questions before I hand over to my colleague Nick, who's going to talk today about you're doing this slide, right?
Yeah, you can do it.
Okay, I can have the slide as well then. Are there any questions about anything so far? Otherwise, I'll go into a discussion about what the lab is and then hand over to my colleague Nick. Any questions? Okay, I'll explain what we're doing today then. So we're going to use this MNIST handwritten dataset. So the handwritten digits 0 to 9. Here's an example of a 9. Clearly a 9, definitely not anything else, even though it's pretty badly written. And we're going to see if we can accurately classify the number that is written. We're going to go over loading the data, so getting this in some way into a machine learning readable format, splitting the data into training and testing sets. So this is how you can work out, is your machine learning model going to work in the real world? You don't have that information just yet, but you have your data set, which you split into 2. You train the model only on one of the pieces of data, and you test it only on the other piece of unseen data. And it's a bit of a sanity check that actually it is doing what is expected. Ultimately, that's where you get your accuracy from, because most machine learning models will be very accurate on the test training data, because that's what they've learned from. They've learned those patterns exactly. We're going to train a simple model on this to do that exact task, and we're going to evaluate this model to see how well it performs using the testing data. And this is an example of what we're looking for. Cool. Over to you, Nick.
Okay, so if you guys have laptops, feel free to follow along. So it is written in a way that you guys can code, and I'll walk you through the code as well. Before I do this, I need to change the display so it mirrors. Is that all right? Is mirror all right?
Yeah.
Cool.
Test data apple colored.
Okay, so everyone should have the README that's been sent out. So essentially, what I'm going to be doing is I'll be walking through this notebook. So there's a example of the entire data science process. So like Sammy said before, it's loading in the data, visualizing it, training a model, and then testing the model at the end of it. So we'll be using a tool called Google Collab. So I've given the link in the README. So if you open that in a new tab, I will show you how that works. So once you open that link, you should come with this screen here. And to have a blank workspace, you can click New Notebook, and that should give you a Jupyter Notebook. So this is an example of a notebook. So essentially, it's a way you can run Python code, and pretty much every data scientist use notebooks. So if I put in example Python, so for example, print hello world, you can run this by pressing Shift, Enter, and it's going to run that piece of code.
You can also click that play button on the left-hand side as well.
Yeah, you can also click this play button as well to run the code. So yep, that's how it works. So like Sammy said, we're going to be coding our first machine learning model. And before we go into the actual code, I'm going to be talking through a few of the packages that we're going to be using today. So there's 5 packages. One of them is called Matplotlib. So essentially what Matplotlib is, it's just a way to visualize your data, essentially. So you can plot graphs, you can plot figures, and you can plot animated graphs as well. So essentially what you need to know about Matplotlib is taking the data, if you want to view it, you're probably going to be using Matplotlib. Pandas is another module. So essentially what Pandas is a way to load in data into something called a data frame. And data frame essentially is a fancy way of saying a table in Python. So it's a table, and you can do lots of different transformations, and it's quite computationally efficient as well. We'll also be using Sklearn. So this is an open source package which has lots of different machine learning algorithms in there. And also it has lots of different useful functions. So you can train algorithms using Sklearn, but you can also evaluate algorithms, and you can also pre-process data using Sklearn. Numpy is another one. So essentially it's another Python library which deals with using numbers, and it's very computationally fast, and it has lots of different scientific computational language in there. And we also have another package called Seaborn, which is like Matplotlib, but it's for visualizing data as well. So we're going to be using the MNIST dataset. So this is an example of, I think, 100 different images on my dataset. So you can see that it's lots of different handwritten digits. Each of them are different. So this 3 is different to, for example, this 3, and different people have written them as well. And the data also comes with labels. So as well as the images, you also have the answers as well.
Do you want to point out that particular number you were looking at earlier? Down.
Yeah, so you have really hard examples as well. So like something like this, I probably couldn't tell you what number that is, but it will be in the answers. So there are the examples that really test the model as well. So something like this, it will probably get wrong, but yeah, it's not as straightforward as you might think. So the first piece of code is going to be us taking the data set from Sklearn. So if I just zoom in a little bit. So Sklearn, we're really lucky we have Sklearn because they have loads of different data sets which are built into the module itself. So from Sklearn, we can fetch OpenML, so the open data sets. So if I copy this over, and I can put it into the notebook. So if I run this.
This copy-paste bit is very accurate to our normal work as well. We do copy-paste a lot of code from place to place.
Yeah, so this is going to take about 20 seconds. So whilst that runs, essentially it's going to come as raw data. So it's going to come in the form as a Python dictionary, sorry. And we're going to be taking the data from this dictionary, which is going to be the actual pixel data of the image, and the target, which is going to be the answers, so the thing we're trying to predict. So that's loaded in. So let me just take the next cell. So if I take the keys here. So right, so we have all of these different data columns, for example, but like I said, we're going to be taking the data and we're going to be taking the target. So we can take those and put those into 2 variables, like this. So we're going to take the pixel data, put it into the variable x, and we're going to be taking the target, the thing we're trying to predict, or the answers, and putting that into the variable y. So if we run this.
Is everyone following along so far in the room and remotely?
Yeah, does it make sense? Yep. Cool. Okay, so just to double check how many images we do have in our data set, we should have 70,000. So we can do the length of our x vector here. So that should return 70,000. And I know it is going to, because I've tested this. So yeah, so there's 70,000 images, just like we expected. So then we can use Matplotlib again to actually visualize one of our data points. So essentially what I'm doing here is, from the Matplotlib library, we're taking these functions here, and I'm going to define a function that I can pass in the x data, and it's going to come back with a picture of what the image is. So essentially what I'm doing is, image, I'm reshaping it to be 28 by 28 pixels, like this, like a square. And then I'm just doing plot.image_show, and because it's a binary image, it's going to be black and white. I'm doing this color map, and then I can use that to plot the digit. So if I just grab this cell here, and I paste that. So again, using the plot digit function, I'm going to plot the first picture in our pixel data. And you can see that is clearly a 5. So essentially, if this works, our y values, which has the answers, the first element of our array of the y values should be 5. So I can double check that as well. So the first element of our target, so it's clearly saying it's a 5, right? So there is one small piece of pre-processing we need to do before. So our targets are in strings, but we need them as integers. So we just need to change the type of our data set. So we can do that by just doing a simple line here. So we're using the Numpy function here, module, and we're going to be using setting y, but as type, and we want it as a Numpy integer instead of a string. So let me just grab this. And run this. And if I do y0 again, that should be an integer now. And we know it's an integer because it doesn't have the quotes anymore. Okay, so now that we have our y's in the correct format, we can also look at our x's. So our x's aren't actually a picture. It is actually going to be pixel values. So if I take the first picture and I just print what it looks something like this. So essentially what this is that every single pixel in the picture has a number between 0 and 255. So if it's a 0, it's basically blank or like completely off. And if it is 255, it's like a black square. So in this example here, you can see everything here, like all along the edges will be 0. And then where the 5 is actually written, these will have higher values than 0. So they can range, but essentially it's a range between white and completely black, essentially. And there are, let me just do the length. There should be, so there are 784 values on the pixels, and that's because we're working with a 28 by 28 image. So if you did 28 times 28, you're going to get 784. And I know we are because I tested that as well. Yeah. Okay, cool. So we've got our data, and essentially the last step we need to do before putting it into our machine learning model is to split the data. So we're going to split it into two different data sets. So we're going to have our training data set, which we're going to use to teach the model what digits look like. And we're going to have a separate unseen data set called our testing data set. So the purpose of this testing data set is after the model is trained, we need a way to be able to gauge how well it's performing, for example. So using the testing set, we're going to be able to say this model is this % accurate, or this %, or going wrong here, or doing this as well. And this is a good test because it's really good to test on unseen data, because if your model is in production, it's going to be seeing data that it's not being trained on. And also, if you test on training data that it's seen before, essentially the model's cheating, for example, because you're giving it the answers and it trains on the answers, and then you're testing it on what you've already told what the answers are. So you need a test set which is unseen. So what we're doing here is essentially we're taking the first 60,000 images out of 70,000 and putting that into our training set. So we have two variables here. So xtrain, which is the pixel data, and ytrain, which is the actual labels, so the answers. And we're also taking the last 10,000 and putting that into our testing set. So the same thing, we have our pixel data in xtest, and we have our actual labels in ytest. So 60,000 in train and 10,000 images in test that we're keeping aside for later. So let me run this cell. Cool. And just to double check, I can do the length of one of these. And that should be giving me 60,000. Yeah, cool. Okay, so everything's set up to train. So again, Sklearn is a really powerful package, and it gives you algorithms in there which are ready to be trained and ready to be fitted. So in this example, we're using something called an Sgd Classifier. And essentially, this is a machine learning algorithm which I'll go over how it fits, but there's loads of different algorithms, right? So there's no correct one to pick off the top of your head. So that your job as a data scientist is to go through as many algorithms as you can as possible, and then try and find the best one that fits the best to your data. Because each different algorithm is going to have different performances, they work slightly differently, and they're going to give you different results at the end of it. So this is quite simple. There's also Xgboost, which is like decision trees. So it will be building like different if statements, like Sammy showed you on the slide. There's also a lot more complicated things like deep learning, like CNNs and things like that, which will outperform quite a lot of things. So what we're doing here, so from the Sklearn package, we're importing the Sgd classifier, and then we are just setting it in this variable here. And we're using random state because essentially every time you import a new model, the weights in the network are going to be randomized. So we need to set the random state here so it allows us to have the same result every time. Because if I don't set this random seed, everyone's going to get slightly different results, but it's not going to be very different. So it could be like your model could be 80% accurate and the next person could be 79% accurate or something like that. But it's good to be reproducible. This max iter is basically the number of times that the model is going to see the training data set. So in this example here, I want it to train fairly quickly for the purposes of this demo, so I've just set that as 100. So it's going to pass the data 100 times through the network, and it's going to learn the digits as it passes through. And then we can also fit the model by doing our classifier, dot fit, the pixel data, and then the real values, the answers essentially. So if I run this, okay, that's going to take about a minute to train. So is there any questions from the room or from YouTube whilst that trains?
Has everyone got to this point?
What's the best way to figure out what classifier to use?
That is a good question. So,
Can you just read questions?
so the question is, what is the best way to figure out which classifier you can use? And that's part of the POC phase that we do. So this is the science experimental phase. So essentially, you can do as many experiments as you want, and I'll probably suggest that you do that many experiments. There are some that are proven to be better than others, but it really depends on your data. So for example, if you had lots and lots of image data, let's say like 100,000 plus images, then you can go down the deep learning route, which is using neural networks and things like that to classify. And that has been proven to be state of the art. So that's going to be a lot better than these shallow learning methods. But if you have, 10,000 images, or even 100 or like 2,000, it's probably better to use smaller models, like for example this one. But you won't know what the best classifier is until you train it and test it and go through all of the proper evaluation process.
Just want to add one thing to this as well. That's absolutely correct. Our job, we only have 4 weeks from start to finish. That's a short amount of time. Choosing the right classifier is important, but it's almost less important than actually getting the right output for the customer. So whatever the classifier we choose is, getting the results understandable by the customer and useful to the customer is more important. So we might not necessarily pick the very best one if we know that there's one that works quite well, that we can then use to demonstrate that this problem can be solved and sorted out. So you can get a very good answer off your first guess, And then Xgboost is one that I use as my initial go-between because it reliably gives quite a good answer. But Nick is right. If you have time and if you have the amount of data, you should try lots of different approaches. Computer vision does really good on image data for this reason.
Yep, cool. And our classifier has trained, so.
So from Slack, could you please reiterate what random 32 does?
Random state, okay. So essentially, every time you import an algorithm, the weights in the network, the things that are going to be tuned over time whilst it trains, is going to be randomized. So if you set the random state as 42, for example, it's going to ensure that everyone gets the same state at the start before training. So the random weights will be, everyone will have the same states. So when you train that, you're going to get the same result every single time. So if you had to reproduce this notebook and reproduce the exact result that you need, it's a good idea to put the random state. You don't have to. If you don't, you're going to get very slightly different results just because the initial state of your model is going to be different every time you start the training process. But it's not, like I said before, it's not going to be massively different. So it could be a few % in terms of accuracy. Yeah. Okay, cool. Thanks. Right, so our model has trained. So we can test our model now. So essentially we can feed in one image at a time, or we can feed in all of the image and do a batch transformation job. So essentially I'm going to be taking one image just for the purposes of the demo. So what I'm doing here is I'm going to be taking the 10th image in our dataset, or the 11th because we count from 0. And I'm going to be doing our classifier, .predict, and taking the 11th image from our test set. And then it's going to print out what the machine learning model thinks the image is. So if I grab this, paste this in here, and I run this. So the machine learning model is predicting a 0, and we can use our plotting function from before to view what the actual digit is. And I hope it is a 0. And yeah, it is a 0. So this is what we fed into our network, and the model thinks that is a 0, and obviously it is correct. So it's doing quite well. I can test a different number. So if I do the, I don't know, the 5th one, the model thinks it's a 1, and the answer is, and it's actually a 1. And just for argument's sake, let me do a different one. Simon, give me a random number. 15? If this is wrong, then I'm going to kill you. It is wrong. So, so that wasn't meant to happen. But anyway, so it's not going to be 100% accurate. So this model, now I have to go. So this model is going to be 100% accurate. So it is going to pick up things. So as you can see from this image, well, how the machine learning model works is it's taking different features of the image. So it's going to take different parts of the number, and it's going to use that signal strength to drive its prediction. So it's probably looking at that image here and thinking that this part here is like very likely to be a 3. If I went like this, it looks like a 3, right? So that's why it's probably driving the model prediction there to be a 3. So even there's going to be numbers in this data set which look very weird, and there could be like different numbers. To us, that's clearly a 5. But like I said, the model's looking at each individual pixel and also looking at the shape and also looking at different parts of the image as well. So it's thinking that's a 3.
Humans aren't 100% accurate, so.
Yeah. Like I showed you from, oh no, it's not here. Like this, right? No one's gonna get that, and I don't even know what that is. Okay, cool. Thank you, Sammy, for picking. You had like a 10% chance of getting one that's wrong.
You said random.
Yeah.
You did run both those cells, right? N equals 15 and then the cell below it?
Yep.
Yep.
Wow.
Yep.
Damn.
Okay.
Sorry, did I say 15? I said 17. Sorry, you must have misheard me.
If this is wrong, yeah, there we go.
Yay!
Back
see?
to normal. Okay, so, right, yeah, so we have our model, but we don't want to test it one by one. We want to do the whole data set, and we want to be able to say our model is X% accurate. So we can do that. So using the same code as before, instead of passing in one image at a time, I'm passing in the entire testing set, right? So you can see here. So this is the entire set of 10,000 images. So if I run this, It should be fairly quick. So that's classified 10,000 images, like in less than a second. So if I do that and just look at our predictions, we should have a prediction for every single image. So this is going to be an array, and it's going to be 10,000 digits long, and each individual element of this array is our prediction for that particular image in our testing set. It all makes sense so far, right? Yep. So what we can do then is we can use the fact that we have our answers from earlier. So if you remember, I said that we put our labels in the Y test. We can compare those with our predictions, and then we can mark how many of them we're getting correct. So what we're doing here is from Sklearn, again, we're importing a function called accuracy score. And then what accuracy score is basically doing is it's looking at each individual element of this array. Let me plot the, show you the array, the Y test as well. 1 second. Right, so essentially what it's doing is it's looking at a prediction, it's looking at the answer, and it's comparing. And it's going to tick it if it's correct, and if it's wrong, it's going to give it a 0, essentially. And then what it's doing is summing up every time all of our predictions, and it's going to count how many times we got right, and then divide it by the number of data points in our sample to get a percentage. So if I run this, and it's going to say that the accuracy of our machine learning model is 82.93% accurate. So that's pretty good on paper. Just, like I said, the state-of-the-art CNNs and the deep learning stuff get stuff like, I think the highest score possible is 99.91% accurate. But that's like using, you know, massive CNN models, deep learning, like lots of different datas and training for ages. Yeah.
How would we make the model more accurate in the future? So that one which got wrong.
Right. So it's probably something to do with the algorithm we're using. So I would suggest either using a different algorithm. Like I said, the deep learning one is much better than this one. Or you could feed it more examples of 3s and more examples of 5s, and then it will get to learn that a bit better. So right now the data is pretty balanced across the whole data set, so it's like 10% each individual digit. But if it's having problems in, classifying, like let's say a 3 or a 5, you could increase those examples, increase the number of examples that it trains from, and try to make it get more information about what makes a number a 3 and what makes a number a 5. Also, we do train it quite quickly as well. We only trained it for a minute. So if you get rid of this max iter thing, you're gonna see that the model's gonna get like, I think it's 5% more accuracy, but it's gonna take like 5 minutes. And I didn't want to wait here for 5 minutes in silence.
There's definitely diminishing return on these things as well.
Yeah.
In fact, actually, there's a thing called early stopping, where if the model doesn't get better after a specific amount of time, rather than continuing to train for as long as you would want to train it for, or have told it to train for, you actually stop it. And in fact, it might be better than if it just keeps looking at the same data set over and over and over again in the long run. Remember, the ultimate goal of this is not the accuracy on that last 10,000, it's the accuracy on the next million on your website. And you don't see that data.
Yep. Okay, so we have this accuracy, but let's say we wanted to dig a bit deeper into what actually is happening in the predictions and where it's getting things wrong. So we can use something called a confusion matrix. And I promise it's not that confusing, even though it's called a confusion matrix. Let me put this. So essentially what we're doing is we are using sklearn again to import something called a confusion matrix. We're calculating it, and then we're going to put it into a table and then essentially plot it. So it's going to make a lot more sense when I do run this cell. So if I run this, it's going to give you this figure here. So let me just zoom out a little bit. Okay, can everyone see that? Can everyone see that? Okay, so what does this mean? So essentially, if you look at the axis, it says actual values, and this is 0 to 9. And we have our predicted values here. So it's 0 to 9 again. And if we take one of these blocks here, so let's say this one. So this is basically telling me that there's 32 times in our data set, in our testing data set, where the model predicted a 2, but the actual value was a 3. So it's getting it wrong 32 times, and it's thinking that a 3 is actually a 2. So again, another example here. Let's take this one here, 0. So there's 0 times where our model's thinking that a 9 is a 6. And there's also, let's say, 13 times where the model predicts a 6. So if I go down here, and the actual value is a 2. So naturally, the times where the model is correct is going to be on this diagonal here. So there's 966 times where the actual value is a 0, and the model's getting it correct as a 0. So this diagonal here is the number of times that we're getting the prediction correct. Does that make sense? So just for a sense.
Got another question, if that's all right, I think.
Yeah.
Thanks. Can you tell how confident the model is in the prediction? So with that 5 that did not come up as a 5 or whatever?
Yes, generally you can. So there is something called a confidence score. So you can use something called predict proba to get the actual probability that it thinks that the digit is a 7 or a 5 or a 6 or something like. I can't do it on this because you can't do that on Sgd Classifier, but you can do it on the majority of the algorithms. So if you wanted to see a score, so let's say for the one it was getting wrong, it would naturally have less confidence. So it might think it's 60% chance it's a 5 instead of something like this 7 where it might think it's like a 95% accuracy. Cool. Okay, so just for a sense check, we can sum this. So essentially, if I take the sum, if I take the sum of this diagonal and divide it by 10,000, which is the number of data points, we should get back the accuracy that the previous Sklearn function gave us. So let me do that. It's very small, so on my screen, so I need to. So if we get 966 plus 882 plus 969 plus 944 plus 826, plus 3 plus 853 plus 773 915. So that's the total amount of times that the model's got it correct from the diagram, divided by 10,000, right? So we should be getting the exact same answer as in the, yeah, so 882.93, and I'm getting 0.8293. So the confusion matrix works. So we can also use this to take a deeper look into the times where our model's getting things incorrect. So if I just use Pandas here to put our predictions and our real values into a data frame, like this, and then I can show you that table. So if I do df.head20, so these are all of the predictions, and these are the real values. So you can see them side by side. So it's getting the majority of them correct. And there is an instance here, so on the 8th image. So it thinks it's a 6, but it's actually a 5. So we can use plot digit to see what's actually going in there. So plot digit. I'm pretty sure, yep. X test, and we're going to look at the 8th one. So yeah, that is quite. So apparently the real value for this is a 5. I genuinely think that looks like a 6. Yeah, so it's this one here, right? So there are places in the dataset where it's going to get it wrong, and it's very ambiguous.
I think the thing to add here is that the people have we've asked the people themselves for the labels. So they've said that that's a 5, but maybe they don't know how to draw 5s. We don't know that. So
yeah.
Depends if the accuracy maybe it's supposed to be instead what a panel of people would actually think this is. So if your labels are bad, your model will also be bad.
Yeah, I did also ask a colleague, and he said that looks like an 8 to him if you draw a line here. So
we can't do predict proper on humans, though. Unfortunately, we tried.
They're going to say 100%, right? But yeah, so that's it for the labs. Is there any questions on what I did or?
Yeah. So you've used that one classifier to process that data. Could you do an illustration of how easy / difficult it is to try and go find another classifier to use for that set?
Yeah, it's pretty easy. So Yeah, but it's going to take ages to train. But yeah, so if I go back to, let me go to Sklearn and I can show you guys the different models. Actually, I can use Xgboost. So
briefly, I just want to say, actually, Sklearn makes it super easy. You just, instead of saying import X, you say import Y, and exactly the same .fit, .predict will work exactly the same way. So Sklearn makes it super easy to actually do this. So it should just be as easy as finding another one instead of Sgd Classifier.
yeah, so let's say I wanted to do Xgboost, which is a completely different algorithm that builds like decision trees and stuff. So I can essentially just do from Xgboost import Xgboost Classifier like this. And then I can just change this in here, right? It's not going to be able to take this because that's a function. So I can do that, right? So now I'm going to change this to Xgboost as well. And this should work. So that's now training a completely different algorithm. It's going to take like 5 minutes, so I won't be able to finish this. But essentially it's that easy. Most of them have like import algorithm and then .fit, and pretty much all of them take in X train, Y train. So you need the data that you're training on, which is the pixels, but it could be anything. It could be like features, like for example, on Sami's slide, he had like age and salary and things like that. So it could be that, and then your actual answers, which is going to be in the Y train. So it's going to be two separate things, and you can do as many different algorithms as you want. But even like the state-of-the-art deep learning stuff will follow something like this. It's going to be a little bit more complicated, but you're going to end up to a point where you do your model or fit, that stuff there. Cool. Is there any other questions?
There's one from Jeff. Explain the line 902 plus 1095 plus 803 plus 931. I'm presuming that's just the total number of data, but do you want to just re-explain that to the audience?
So explain this out here?
Yeah.
Yeah, so, so essentially what we did before, so I did the accuracy score by using a function in Sklearn. So essentially what it did is took the predictions and then it compared them, and then it ticked it when it was correct, and then when it was wrong, it gave it back a 0, and then it just summed everything and then gave you, out of all 10,000 examples, what percentage are you getting correct? And the answer was 82%. So just as a sense check, to make sure that's correct, I did it the long way, which is using this confusion matrix. So the times that the model's getting it correct is on this diagonal here, which is the numbers that I'm summing up in the cell below here. So you can see 966, 882, and then so on and so forth. So I've summed up the amount of times that we're getting it correct, and then I'm dividing it by the total number of examples in our data set. So that's going to give me back the accuracy, which is the exact same accuracy as I got from the one-liner from Sklearn, which is 82.93.
Yeah, just one other thing I wanted to mention, actually, mind if I just go to this slide, about reading this. So yes, Nick is correct. This is the correct answer by the people who gave their own labels. But where you can see like more density, that's also like other misfires here. And yeah, there's some weird ones like, okay, this 8 looks like a 6 or a 5, whatever. But the most density away from that diagonal is 2 and 3. So that kind of makes sense in your head that, okay, an 8 and a 2 and a 3, there is some overlap between those shapes. Not with the 4, there's very little here, but there's some here. And you can kind of see it here as well. So with a 3 and a 5 according to the model, you saw also that I've been told my 5s look a lot like 3s. So that would make sense why humans struggle on that. So obviously also this machine learning model is doing it. You can see it here with 4 and 9. You can see some people, the way they might draw them, there's also some overlap there as well. So it kind of makes sense, and there's a nice way of looking at that data at a glance. If you just saw one digit in isolation and it was predicted as a 5 when it wasn't a 5 or vice versa, it would be a bit hard to work out why. So these false positives, false negatives, what you want to call them, are good ways of looking at what's going on here. There's also a question I wanted to add as well, but I need to go back to my laptop, I don't know what it was.
Yep.
Can you incrementally train an Sklearn classifier over time as you get new data, or do you have to keep using the raw data and perform a fresh training every time?
So you can increment. So essentially, if I fitted the model once, I could save that model, load it back in later, and then continue training afterwards if you get new data in. So that is definitely possible.
There's also something slightly related to this. I think I talked about the human in the loop aspect, but if you have labels with your new data that comes in, or if you have the examples with really low confidence scores, if the thing's finished, you should do the problem, by the way, to show an example. If you have really low confidence scores, you can send that to a panel of people to say, is this a 5 or a 3? And then that data, once it's been labeled that way, can go into the pool of data as well. So your data should grow over time, with caveat that if the patterns in the data change for whatever reason, then maybe that's not suitable for your future training model. So in this example, it's kind of less relevant. But if I'll give a silly example, if the way that people draw sevens goes from a 7 to a 7 with a dash through it, this model is going to get it wrong because it doesn't know that that's a thing. The data before and after COVID-19 in financial services data or airline data or ticketing data, cinema data could be different because people have changed the way they behave. And that might mean that just using the new data as well as the old data actually makes it worse than just using the new data or just using the old data. So it's worth bearing all these things in mind. In this example, I think the 7 with a line through it is probably the best example I have. It could be that in a particular country, people write 7s that way consistently more than they do in the UK or in an English-speaking country. And so 0 with a strike through, for instance, that sort of thing. This model might not do very well on that. So just in refreshing with the new data, if you didn't have labels, might not help so much. Sorry, I took a long time.
Yeah, it's not going to finish.
Still training? All right.
Last time I tested Xgboost, it took 15 minutes.
So there's some reasons to not use Xgboost, but it is a powerful model and it is kind of, it fits a lot of use cases.
I can keep this running. If it
why
if it stops while we're having pizza, then I'll come and grab you.
Great question, Dan. Thanks.
Cool. So if there's no other questions, I'll hand over. Yeah, go on.
So you've done your model and you finally want to put it out to production. What's the typical process of getting this into production?
Great question. And don't forget to reread the question.
Yeah. So the question is, you've got your model. How do we take this model into production? What is the process behind that?
You would not put this model in production, though. It's not,
yeah.
it's not that great, unfortunately. Yes.
So let's say you have the model. You have the model in the notebook. You've tested it. You're happy with the results. Essentially, what you can do is you can save the model as a model artifact. So essentially, it is just saving it as a file. So it could be a zip file. It could be a pickle file. And you can use that to load that back into Python later when you're in your production environment. So essentially, what the workflow would look like is you would have, let's say, data coming in, right? And let's say you had to do some transformations to the data. So let's say in this specific example, you had people taking pictures of, like writing digits and taking pictures of it and trying to put it past it through our model. So essentially, we need to make sure that before the data goes into our model, it needs to look like our training data because that's what the model is used to. So you'd have to like grayscale it, resize it to 28 by 28, do all of that stuff. So there'll be like a pre-processing element in Python. It could be in a Lambda or just in any cloud service you want. Once you get it in the right format, you can also use Python to load your model back in from the model artifact, so because you have a file. And once you load that back in, you can just do what we did here, essentially this here. So you would have like model equals some like load model function, right? And then the file name. And then you can do model.predict into the thing that you're trying to pass through in production. And then that will give you back the 7 or the 6 or whatever. And then you can do some post-processing. So for example, you could have a piece of MLOps that looks at the confidence. And if the confidence is too low, then maybe that needs to be checked by an external reviewer. Or you can do like, if you want to put it in a table or in a visualization where you can have a dashboard with a picture of what you pass through and the prediction and things like that. So it's fairly easy to put this into production. So you can save the model, load it back in, and just you don't have to retrain it or anything like that. Cool. Any more questions? No? Sammy, do you want to wrap up?
Sure.
Cool. Sweet. I'll let this keep running just in case it finishes.
Now I need to find the presentation, which is always a pain. Okay.
You need to change the mirroring as well.
I'll be fine. It's just one slide. I mean, do you want to talk through that, or is that all right?
You can do it. It's fine. I've already pretty much said.
We talked about most of these things. I think it's worth just putting on to explain that this is what convolutional neural networks look like, CNNs. It's an architecture that was. Let me just do regular presenter view. Actually, that should work. I think. Nope. Yay. Okay. So it gets a lot more complex. You can see there's many stages here. It's actually quite easy to set these up in PyTorch or TensorFlow or whatever other deep learning neural network architecture you would use, but that's what a computer vision model looks like. And what it does is it takes these sort of blocks that scan across an image to find if there's a feature in an image. So rather than, we're lucky in our example, we have the 1 is in the box like this. What about if there was a 1 in the bottom left-hand corner of the screen and you wanted to detect that rather than just if there's a 1, like a massive 1 covering the entire screen? You'd want to find if this 1 was anywhere within the screen. So you'd have this sort of block that scans across the entire image. In this case, it's trying to find whatever feature is in this picture of a car. The feature might be a car, by the way, but it's looking for something. Let's say it's looking for this headlight. So it's going to scan across all of this. There's lots and lots of different poolings here, like trying to get this information to be combined, and it's changing the shape of the image, it's creating extra information. And then there's this fully connected neural network, which is cells that are connected to every other cell. It gets extremely confusing, to be honest, and is based on how we thought that the brain actually processes images. Turns out, actually doesn't work like this in the brain. I did a neuroscience PhD. If you want to ask any questions, please feel free. But it was a good enough approximation that before there was a canonical problem in deep learning of image classification or like captioning, like what is in this picture? Is this a panda? And humans were a lot better than machine learning models. Like machine learning was like 50% accurate, 8% accurate. Humans are 95, 98% accurate. And then somebody called Alex made something called AlexNet that's based on this and was well past the human accuracy. And now it's gotten to absurd levels of accuracy where we can be confident it is this particular human in this particular picture and very low resolution here. In this case, this person's building a classifier because right at the end, this softmax step, they're saying, is this a car, a truck, a van, or whatever else? And one of the fields would be panda in this case. And it says, okay, is this a panda or not? So training this will take a lot more data, it'll take a lot more time, it will cost a lot more money, presumably, to actually run the thing. Although, remember, you could use your GPU accelerated instance from Google for free as well. Hint, hint. The only stipulation there is they will kick you off after 12 hours, and they don't want you to Bitcoin mine. They do please politely ask you, please don't mine on this. But otherwise, it's a free GPU instance for you to use. We use GPUs to train these because these architectures are all, or they involve lots of matrix multiplications, and it turns out video games also involve lots of matrix multiplications, so it's almost the perfectly tailored hardware for this, and the main graphics providers, NVIDIA and AMD, they made a play towards getting into this space. Good for us. It makes it quite easy to do these sorts of things. You don't have to think about this when you're doing your machine learning model. That said, you don't have to build this. You can also just import AlexNet. There are repositories that contain those sorts of models that you can just say, hey, I want to use this. And they say, yeah, sure. You can even train this specific algorithm to detect some extra use case you want. So you can take this and add another thing at the end of it and say, I want to know just, is that Sammy in the picture or not? And obviously this model will not, hopefully, will not specifically know me unless it's got a picture of me somewhere. And that's called transfer learning or fine tuning. You can use that approach there. At my previous company, where I did deepfake for voice, so I was with people's consent, I was copying the sound of their voice with very small amounts of data. I came almost concerningly close to my voice after 5 minutes of phone recordings, when the gold standard is 20 hours of studio recordings, because I used someone else's studio recordings and then just said, okay, and then this is what I sound like. So what this is doing is it's trying to understand what is an image, what is a feature in an image, what is it that is important about this image for sight, and that is almost irrelevant to is this a panda or not. Just right at the end of it, you just need to say, great, and also, is this a panda? That's essentially what this is doing here. So that was a long explanation of the first point. But yeah, these models can get absurdly high accuracies. And by the way, CNNs are one type of modeling. There's now, if people have heard about GPT, general purpose transformer neural networks are another play into neural networks that have nothing to do with the way that the brain works, but have outperformed human brains and can come absurdly close. So you can get transformers to do image analysis. And actually, one of the main technologies we used at my previous company was something called Fast Speech 2, which was a transformer for speech synthesis. It's like a transformer neural network creating things that have nothing to do with the way that the human auditory system, hearing system, or visual system, or the brain of those connected to those parts has anything to do with it. Pretty stunning, to be honest. So that's one aspect. The second is, this is a very contrived use case, 28 by 28 pixel. It's not very likely that you'll have somebody just right within that sort of grid. You might have a check that contains lots of digits, so how to get those individual data points there. So at least you might want to use color in your data set. Lots of these algorithms can handle that, and you probably would want to use that. Regardless of what approach you would use, you would want to train for longer. Maybe you get more better results if you, rather than stopping after a very short period of time, allow it to train to completion. Jeff in the Slack, who works at ECS, trained it without this early stopping parameter and got it to 87% accuracy using the exact same code that we ran instead of 82% accuracy, which if you use the random seed 42, you should have got. And this adversarial examples, we talked about that example there, but yeah, making it a bit more robust against 5s that are really 3s and 3s that are really 5s. You could do that for this. That's us. Are there any questions that anyone would like to talk about? Otherwise, we've been Sammy and Nick from ECS Data Science, soon to be Global UK&I in data science, and we're happy to have presented our very first takeover of the DevOps Playground as a data science playground. And yeah, very keen to hear if there's any interest in how to productize these models using machine learning, MLOps. Yeah, there are many ways that we could take what we built and actually deploy it into production. We've talked about one example, many other examples, and some specific to the cloud. But yeah, this is just the starting point. This is hey, it's cool. We've built something that's close to being good enough. What could we do with it in the future? Thanks everyone for your time, and enjoy the pizza and beer if you're in the office. Stay? Oh, photo, sure.